Hello all, welcome. This is Mr. Mays coming to you, as always, via the digital, brilliant metaverse, etc. And through Gigabyte, or at least through Data Drive, we will be talking about combining and transforming discrete random variables. All right, this is 4.2. It is brilliant to have you. I'm doing this over our long weekend with the understanding that thankfully this will be my one shot. Well, not thankfully this is my one shot, but thankfully I have a shot at doing a little bit of teaching this weekend. Otherwise, I've been going bit by bit, slowly insane. But thankfully, I'm brought back once again by the brilliance of statistics. So let's talk about combining and transforming discrete random variables. It is brilliant to have you, wherever you're queuing in from. And what I want to do is I want to start by sliding ahead to slide 20, okay? Which is our title slide. All the previous slides are going over information. They also have the warm-up slides on slide 19. This one should not be too difficult. And after today's lesson, if you did have any troubles with the warm-up, you should be able to go back and get those done without any struggle. If we move over to slide 21, we see Pete's Jeep tours, right? I can't draw a Jeep. I'm actually noticeably bad at drawing just about anything. Although vehicles you would think would be easier, but here we go. This is Pete's Jeep tour. And that's the Jeep. Boom. Okay. We know that he's in a tourist area. I always talk about it like it's an island. But there must be at least 2 people in the tour, and the Jeep can hold up to 6. So we already know our outcomes. And as you can see on slide 21, it says what is the expected number of passengers, and we have it mapped out 2, 3, 4, 5, and 6, right? We also have the probability of him having that many passengers on a given tour, right? So those probabilities, as we know, because it is a valid distribution, we know that all the probabilities add up, I should say, to 1. We're aware of that, right? Because it's one whole distribution. And if we pop ahead to slide 22, we have our equation for transforming random variables, right? Because last time we were talking about all this, we looked at, different ways that you can calculate, for example, a mean of a distribution, right? But now we're looking at, well, how do I transform that mean, right? And this is very useful because sometimes instead of knowing the number of passengers on Pete's Jeep tours, and I said this in class, what if we want to know the amount of dollars he's raking in, right? Dollar bills, y'all. And if I want to make that transition, I need to be able to transform my data. In essence, turning all of my passenger counts for outcomes into monetary values, right? Dollars. And as you can see, the equation here is the same as it's always been for transforming the mean and transforming the spread, which is y equals a plus bx. And this will apply when we are transforming the mean. Or the center, really. Any center measurement will follow these values, right? In this case, the key to be aware of is that y is actually the new mean that we're looking for. X represents the old mean, the one that we currently have that we're transforming. So in this case, the old mean, our x here, would be the mean number of passengers we calculate, right? Versus the new mean, y, would be the mean amount of money that we rake in. A and B, on the other hand, I'll use green for that. B represents the multiplier, right? It's the value that you're multiplying your mean or each data point by. And A is the add or subtractor, right? And all that means, and again, these are not terms like that we necessarily need to use, right? But it's just to remind you, right, that value A is being used to show the number that we're pulling away from or adding to our values, right? So that'll be how we transform mean. And to go slightly forward, and we're still on slide 22 for this. For standard deviation, it's the same idea, but what we do is we take the new standard deviation and we admit that the old standard deviation times our value B is what we have to put together to get our new standard deviation. So this is our old standard deviation. This will be our new standard deviation. And B is just our multiplier, right? Because we do not add or subtract from our standard deviation. We only multiply or divide by our standard deviation. And we do absolute value for standard deviation. Why? Because standard deviations are never negative, right? You can be negative standard deviations from something, but the standard deviation itself is not actually a negative number. It has to be positive. All right, and we should know that the shape of the distribution never changes because of these values, right? Slide 23, I go through all these rules again. Slide 24, I ask you to run through these calculations with the understanding that you've already calculated your expected value, so your mean for Pete's Jeep Services is 3.75 passengers. And your standard deviation for Pete's Jeep Services is 1.09, right? I give you that standard deviation. You're not going to have to calculate it, but you were supposed to calculate the expected value. Now what you're going to do is you're going to fill in that chart below. Just make sure you understand that for each of this, it says Pete charges $150 per passenger. Now, as a critical thinker, when it says per, and then it says the outcome measurement, sorry, I have something in my throat. When it says per, and then it says the outcome measurement, in this case, passenger, I know I'm multiplying. Right? It's either going to be multiplying or dividing here. And because it's $150 per passenger, we're multiplying each passenger by 150. So to figure out the money collected, you'll do 2 times 150, 3 times 150, 4 times 150, 5 times 150, and 6 times 150. And those will be the new value dollar amounts for each passenger. The probabilities will stay the same, though, because those probabilities have not changed just because you're looking at the money now as opposed to the passengers. Now, wisely, I'm going to stop you because I know you can do this now. And I'm going to say, what is the new mean, right? We have our old mean, and we know that we are charging $150 per passenger. What is my new mean for Pete's Jeep Tours, if we're looking at dollars now? Go ahead and pause the video. Okay, and you've unpaused now, and you should be feeling pretty solid. What did you do? Well, I know what you did, okay? You looked at A plus B times X, where X is E of X. So your new mean was equal to A. Did we add anything? No, we're not adding anything at all, so it's 0. There's no change there. Plus B, which is 150, that's how much we're changing it by, times our old E of X, which was 3.75, we calculated, right? And this yields you your new answer, okay? I'm going to calculate it because I'm not doing that in my head. I should, though. Ugh, I wish I were in the right headspace. It's too early. Daylight savings time is messing with me. It is $562.50. And that will be my new mean when I'm looking now, instead of at the number of passengers, at the amount of money raked in. And that should make good sense. And then I say to you, pause the video and find the new standard deviation. And you have done so. You have paused the video. You've found the standard deviation, I hope. And you will find that the new standard deviation is equal to the absolute value of B times the old standard deviation. You've gone and you've said, well, therefore the new standard deviation equals the absolute value of 150, which is just 150. Here, absolute value literally only means get rid of the negatives, times our old standard deviation, which is 1.09. It's been given to you. And that gives you our new calculation. It's like 100 and something. Let me see, 1.09 times 150, 163.5. And that is our new standard deviation. Okay, take a second, mull over this brilliant data, understand what's happening, recognize that what's going on here is essentially we're just looking at how things will alter our center and our spread based on a multiplier. Okay, we then have the same problem moving on to slide 26, but we do adding and subtracting. You'll see we have the same values posted up, but now it says it costs Pete $100 per trip. When I see cost, and I see per, and now I see trip. Trip is a measure of our whole distribution, right? Our probabilities, when they add up to one whole, that's one whole trip. Does that make sense? And that's important to notice. When it's the whole distribution you're talking about, right? Per trip, that's when it's add or subtract, right? And it says it will cost. When it says cost, that is a minus. So we are subtracting 100. Okay. The key here is to remember we will subtract 100 from our mean. To get 462.50. But we will not subtract 100 from our lovely standard deviation because standard deviations do not respond to adding and subtracting. So this will stay the same. And that's it. When it says expected profit, it'll be 140 or 462.50 because I've found my expected value for money and then I've subtracted the cost. And then I don't have to change my standard deviation because losing $100 from everything does not alter how far apart our values are versus multiplying everything by a different number does affect how far apart our values sit. Okay. And again, logically, this should all make sense. He's losing $100 on every one of his money collected. If you look at his profit and you look at, on slide 26, all the money collected outcomes, we have 300, 450, 600, 750, and 900. Our profits, when we subtract the 100, will apply as follows. 300 becomes 200, 450 becomes 350, 600 becomes 500, and so on. Okay, the final big thing we must go through here on slide 27 is what about if we have two distributions? And again, this shouldn't feel too terrifying, okay? Now I'm gonna use X and Y to represent my two distributions, okay? So we have Pete's Jeeps, which is Xi, and we have Aaron's Jeeps, which will be Y1, or Yi, I should say, right? And it looks like we have means and standard deviations for both of those, right? Pete's are at 3.75 I should say, and Aaron's are at 3.10, okay? That's the means, I should say. Okay. It says, one, what are the possibilities for X plus Y, right? And the possibilities for X plus Y are simply as follows. You're gonna take their passengers, right? The different X values, and you are going to add them together, right? Simply put, you're going to add them together. Because E of X plus Y is equal to, and this is on slide 28, E of X plus E of Y. And notably, E of X minus Y equals E of X minus E of Y. And that's it. That's all you need to know. Is that one, when we're subtracting or adding distributions based on their passenger number or their outcomes in this case, right? We're just gonna add them together, each one, or subtract them. And if we wanna add or subtract means, we'd do the same. So we would just say, what's the mean of both of them jointly? We would say 3.75 plus 3.1, and we would get 6.85. As our new mean. And if we wanted to subtract, we would do 3.75 minus 3.1, and we would get 0.65. So those are our rules for means. Now, the key here is if we subtract two random variables, we are also subtracting their random values. We are also subtracting, so to speak, their expected values, which we know to be the mean, right, of each probability distribution, effectively. Now, when we look at standard deviation, it's similar. It's almost exactly the same, but there are two finicky things about standard deviation. One, we don't add standard deviations. We add variances. And variance is standard deviation squared. So as you see by your equation on slide 29, if you want to add two standard deviations together, right? In this case, I'm going to use Pete's and Aaron's. Pete's standard deviation, right, is 1.09. And Aaron's standard deviation is 0.943. If I want to merge those together, what I have to do is I have to do the variance of them first. Which will come out to, and now I got to do my calculations. You should do them along with me. right? 1.09 squared, which is 1.19, I'm going to say. I'm going to round up from 1.1881. And then 0.943 squared. So we're adding to that 0.89, we'll say. And this is exciting. Look at what we've done already. We're merging standard deviations. So we simply take that, we add them together, and we get 2.079-ish, right? And then what must we do? Well, that's equal to our variance, which is sweet. But if we want the new standard deviation, we now have to square root it. Okay? So that would make our new standard deviation of our merged values. Into 1.44. Okay. So the key things to be aware of so far are that when we do standard deviation and we want to add those together, we have to square both the values first, then add them, then find the square root to find the merged value, as I've done here. You can't do it in the other order, you don't get the right number. This is because variance is far more important and far more exact to look at spread than standard deviation is. Standard deviation is super useful specifically for normal calculations, right? Okay, we have this value. Last thing you need to know. Last big thing, I should say. There are a few more things I want to go through and a lot of practice problems, but things I want you to know. You cannot, never subtract standard deviations or variances. Don't subtract them. If you have a situation where you are subtracting your means, you should be adding your standard deviations, not subtracting them. Right? Why? Well, not adding your standard deviations. Oh, Mr. Mays, a faux pas. Send him to the guillotine. You do not add the standard deviations. Even if you are subtracting your expected values, you should add your variances, and then you can square root it to find your standard deviation. Why? More variables equals more variability, which equals, in turn, more variance. And even the first part of this equation I'm writing up for you is more distributions. Even if we're subtracting one distribution from another, we are complicating the situation. And by complicating it, we are still going to add. Always, 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 always. We cannot add standard deviations. We can only add variances, but we cannot subtract variances or standard deviations. As you can see, if you go on to slide 30, I ask you to find the expected values for each of these, right? Should not be too bad, should not be too hard. And I'm going to make sure to post up the answers as well. But you should be able to compare these and understand them pretty with a lot of assurity, I should say. You get to slide 31, and you see once again the rule that I just told you, which is that you cannot subtract variances. Even if it's variance of x minus y, you are adding your variances up. We move on to slide 32. I have you find, once again, your expected values based on the values I'm putting here together, right? And then I have multiple choice questions. On slide 33, we went through, we calculated, hey, what was the situation there again with our variance and with our standard deviation? You should have picked answer C for slide 33. That's the one where we square the values, add them together, even though we're subtracting the distributions, and square root the whole thing, right? You should have seen on slide 34, once again, our right answer was C. The maths out. On slide 35, I have some Khan Academy magic for you to look at. Not as good as our stuff here, but just if you want some added practice. And then on slide 36, I have our magic takeaways that I want you to have sitting at the back of your mind. And those takeaways are as follows. We add and subtract a constant from random variables. It changes the mean, but not the standard deviation. Okay? Add, subtract, only the mean, right? Multiply, divide, changes standard deviation and mean. Right? And when we add or subtract two or more random variables from one another, right, the distributions of those variables, we add or subtract the expected values. But if we are adding or subtracting, I should say, two random variable distributions from one another. We only add our variances. We do not add our standard deviations, and we do not subtract our variances or our standard deviations. Okay, from the slides 37 all the way up to 50, I have different calculation problems for you to look at. I will be posting answers to these in the near future, but do go through them, do practice them. We may go over them next class is what I'm starting to think as well. So do your best work. I believe in you. I am so proud of you for coming in and looking at these video notes. You can see that our battery power did not slide down this time to the near 0% range. But I thank you. I thank you for looking at statistics with me, for hyping up this joy with me, and for understanding the way that we handle two different distributions in terms of our expected values and our standard deviations, and then how we transform distributions in and of themselves. I hope this makes sense. May Pete's Jeep Services stay with you forever in your heart. Remember for always that this is how we do these kinds of calculations. Do not forget probability. Practice it often. And I adore you. And this is Mr. Mays signing off.